Hi guys, today we'll be exploring our hash table. We'll be programming a simple hash table with no collision mechanism. Just insert, delete, lookup, and the hash function, and we'll see what happens when collision happens and there is no collision mechanism. It's the most basic kind of hash table that you can program in interview without collision mechanism. Okay, the advanced hash tables have collision mechanism that we'll explore later in the other videos, but in this video we'll just be exploring a simple hash table with no collision mechanisms. Just insert, delete, lookup, and the hash function. So first of all, you can see here we've got a max name that actually means the maximum size of the name of the fruit. As we'll be working on fruit tables of table of fruits. So like we did in the conceptual explanation of hash table. The table size I have taken as 10. One can increase the table size if one wants to. One can also increase the max name if one wants to. Right now I'm just keeping the hash function as a string length, just a string length of the name. Okay, it's just to give you an idea that how hashes can be calculated. String length can also be a hash function which can calculate the index, the hashed value uh, on the table, or the index on the table. And so we have got here fruits like apple, banana, kiwi, orange, and mango, and we'll see what their hash values comes out to be when we execute it. So we have compiled it. Let's see the output. And we got 5, 6, 4, 5, 6. So for apple 5, banana 6, kiwi 4, mango 5, orange 6. So that's the current hash values or the indexes on the hash table if we create a hash table right now. But we can improve our hashing function, and for that what we'll do is, right now it's just running string length. Let's improve it a little. As I already said, there's no perfect formula to create a hash table. You can try out whatever you like. I'm just trying something out here. So what I'm trying to do is I'm trying to run a loop, and I will save the ASCII values in the index, like something like this. So and and then I'll return the index. For the time being, let me comment this part out, and we'll see what the output comes out to be. So well, now we have different kinds of output: 530, 609, 436, 530, 636. But these values do not fit in our hash table. They are very big for the table size, because table size is just 10, and these values are big. So we need something that keeps them contained. So as you know, the table size is 10, so we need the values to be within 10. So now this part of the code, index is equals to index modulo operator table size. This part of the code actually gives us values that are within table size. So this actually returns the this index modulo operator table size returns us the remainder, and which will always be within uh, our table size 10. Well, let's execute it and see what happens. So if we compile hash table and we see the output, so you can see 09606. all the values are now within 10, so they can be represented on the hash table. So well, let's now build a structure for our hash table. We'll keep the struct's name as fruit, as we are working with the fruits. Now we'll declare a hash table. That will be fruit pointer hash table, table size. So why do we have a fruit pointer here, not fruit? So hash table becomes an array of fruit pointers, or a pointer array. Well, a pointer array is useful in hash table because it represents two states naturally for each bucket. Empty means null. Occupied means there's some address that points to the item. In our case, it's a fruit. Again, the pointers are easy to delete and easy to remove. Now, if you have fruit, not a fruit pointer, fruit, so those that can also work. But if the struct is small, then it's okay. If the struct is big, then the hash table size explodes. Okay, because now you're saving the whole struct. The hash table size will explode. It will become very big, and then deleting and adding will become difficult. Whereas in case of pointers, it's far more easy, right? So next, we'll be building the initialization of the hash table and print of the hash table. So let's initialize the hash table and print hash table. So for initialize the hash table, we'll run a loop of the table size, and uh, to initialize the hash table, we'll put each value as null. So hash table for each position will be equal to null because there is no value. And in case of print, we'll just print it in the same way, and else. So if it's null, what we'll just do is we'll just print I, and we just print some minus 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 to show that that position is null. If that position is not null, then we'll just print the name there, so that uh, we know who is occupying that particular position. So now if now we don't need these, we can just comment them out, and we'll call init hash table, and we'll call print hash table. Let's execute it and see if it's getting executed or not. And we see all the values are empty, there's no value inserted. Now, so let's create some struct objects. Okay, so first of all, fruit, apple, so now we created all the fruit objects, and let's delete these are of no use now. Now what we'll do is we'll start inserting them. So insert hash table. Oh, we didn't build the insert hash table, so let's build the insert hash table function first of all. So insert hash table, and we'll take root. The first thing we'll need the index, which we can figure out by sending the name to the hash function. And once we have the index, we'll check hash table index not equal to equal to null. Okay, if it's empty, else not empty. So if it's empty, then great, we just have to do hash table. If it's empty, if it's not empty, then we return false. That is, the insertion failed, because right now we don't have a collision mechanism, so insertion actually fails. So what we do is we'll form an if, and we can just keep a check, printf success, right? So let's do this and see if our insert is working or not. So we got success down there, you can see there's success, so it means our insert is working. What we'll do is we will, for the time being, not check these things. Let's keep it simple and insert all other fruits. So now you can see we have inserted all the fruits, and to see if all of them got inserted or not, let's just run a print hash table and see what happens. So, oh, that looks a little weird. I need some kind of start and end in the hash table that will make it good enough, or visible. The visibility will get better if we get some kind of start and end in the printf. So you can see initially the table was completely empty, there was nothing, but then you find apple, kiwi and banana in the table, but there is no mango and orange. What happened with mango and orange? Well, they actually had collision, and because the bucket was already occupied, they got lost, because there's no collision management mechanism, so they got lost. So in this code we don't have any collision management mechanism, uh, as that's not our aim right now. um, we'll be building that in the next video, or the next yeah, in the advanced hash tables. Right now we have got insert. We'll also try to do delete. For delete we'll have a fruit pointer. Now why am I having a fruit pointer here? uh, because if we are successful in deleting, okay, then we send what we deleted. If we are unsuccessful in deleting, that is we didn't even find, then we just send null. Okay, so the first thing is we have to perform, again we have to figure out the index, HTable index, and this time we want to find that does it exist at that index. Does something exist at that index? If something exists, then the next thing will be to do string compare, and there it has to work out with hash table index name, and the, sorry, it should be character name, because we are comparing the name and we are just sending the name. We're not sending a whole structure object. We'll just be sending the name to delete it. And so max name, the maximum size of the name. And also because strncmp xtrncmp returns 0 on success, we'll put a not sign that will make sure that if it's 0, that it's successful. In the end becomes 1, so that our ending operation becomes successful. Now If that does not happen, then we return null. And if if you're successful, that is, we found the variable, found the structure object pointer to delete, what we'll do is we will need first of all a temporary pointer. Now, why do we need this temporary pointer? We are sending the fruit pointer back, right? So we need to send something back. So think like, I mean, if the data gets, or the fruit gets deleted from the table, obviously at that position it should be null. Okay, that's the thing. But what did we save here? This was a pointer to the fruit structure. Okay, temp. We return the temp. So this temp actually carries the fruit that has been deleted from the table. Right now we are not doing anything with the data here in the code, but in the future scripts, or sorry, in the future codes, it will become useful. For the time being, just understand that this is just sending, this is a way of sending the fruit or the item object, struct object, from this function back to the uh, function where it was called. So for example, after print, I call delete hash table, and we had kiwi, so we'll delete kiwi. Okay, so I need to delete kiwi, so I need to send kiwi. Okay, now the kiwi will get deleted. And also, to know whether the kiwi got deleted, we'll just again print the hash table. So uh, compiling, there's some kind of mistake on line 60. Oh, sorry, name. So you can see the kiwi was there present, but now the kiwi is gone, so kiwi got deleted. So delete worked perfectly. That was great. uh, well, we need one more function, that's the search or lookup, and for that we'll also have same, like similar to delete, the lookup hash table char pointer name. So this lookup function will actually return the will return the fruit object if it's found. If it gets found, we just return the fruit object. If it does not get found, we return null. And yes, the fruit object gets found, we return the hash table uh, index. Yeah. So let's see if our lookup function is working. So what we'll do is, after delete, we'll just run a lookup hash table, and we'll look up for apple. Okay, and we'll save it in a fruit f, and we'll print the value. So print the val, and if we get the right val, then we should get 10. Then our lookup is also working fine. We got value 10, so lookup is also working fine. So guys, that was our simple hash table. It had uh, a struct, a fruit pointer hash table, an array of pointers, a hash function, initialization of the hash function, printing the hash function, inserting, lookup, and delete. We did not have collision management mechanisms, and the reason it was not it was avoided because it's planned for the future videos. Thank you, and please like and subscribe, because that gives me motivation to keep going. I hope it was helpful. Thank you.